Okay, everybody, welcome. Sorry for starting a little bit late. So how did Project Zero go? Was it exciting?
I'm
Yay,
hoping
right?
that I set it up correctly in Git.
Okay, so maybe not that exciting. Git's the worst part. Okay.
I'm fairly sure that I got everything working correctly. It's just I don't know if I set it up properly for that. Roughly how long will it be before we know if we got it right?
So the graders are still working on the scripts, but it's supposed to be by the end of the week that we should have the grades by like Saturday.
Okay, so if I get a 0, I know that I did something wrong again.
Exactly, yeah. So if you get a 0, you know something went wrong in the chain. So it was either, you can use the test cases to see if you got it right. If it's not that, then you can check the build system. If it's not that, you can check Git. So I did a little demonstration for some students who came to office hours of GitHub. So GitHub is just one way to view Git repositories. Well, maybe to step back even a little bit. So Git, just like any version control system, so who wants to be a software engineer? Has anyone got to do software engineering or programming? Not many. Okay, most maybe? Or version control is like industry standard. Any reputable place is going to have version control. And I chose Git for this class. It's what I'm used to. It's one of the most popular ones. And even if you've used version control, you may not be used to doing it on the command line, perhaps. Yeah. But I think it's useful because it gives you a very intimate knowledge of how this version control system works. So who can tell me what version control is? Any takers? Who knows? Who's used it before? Who can tell me? Yeah, in the back.
I'm sorry, can you say the question again?
Who's used version control before and can tell me what version control is? Okay.
Essentially just keeps a log of everything that you've done. So if you want to say, I want to go back to the way that this line was exactly 3 months ago, it essentially starts with like an empty blank file, and it says the first time you commit, you added these lines, and then every subsequent commit, it's like it just stores whatever the changes were. So it kind of rebuilds those changes as you go through, and you can stop it at any point and kind of pick and choose which changes you want.
Yeah, so that's exactly right. It's a log of the changes that happen to your entire code base. So on GitHub, you can click on this commits history here, and it'll show you a log of all of the messages associated with those commits and a hash code, part of the hash code for those commits. So each commit is given a unique identifier, this hash code identifier, and they're chained together. So it's a log of these changes to the code. So typing git log will show you those changes to the code. The top commit is the latest version of the code, and you can see head is just a special, is just whatever the top of the log is. And you can see that the tags, we have tags here. But really it's just a list of changes to the code. And you can actually see in GitHub, you can either browse what the code looked like, just like your classmate said, browse what the code looked like at that point in the history. So this is what my code looked like originally. It was just one README file. In the second commit, I changed the README. And you can even view diffs of these commits, like the differences between the two commits. So if I click on the actual message, it shows on the left what was changed in the previous file, and on the right, what was changed in the new version of it. So it says some line was removed in readme.md and some line was added in readme.md. Okay, so that's like the basics of Git. And then these are, each person's version of this repository is equally as authoritative as anybody else's. It just so happens that if you choose that the GitHub version is the official version, which we're doing in this class, then that's the official version. But there's nothing in the technology that says this version, this copy of the repository is like the real one. So that's why you can go out and you can fork a project, you can just clone it yourself and make your own version of somebody else's work if it's open source. Okay, so so the way I had you submit projects is to use Git tags. So tags, as I showed you in this Git log, It's just a name that you assign to a particular commit. So if I tag this first commit with test tag, no matter how many other commits I add, I can always easily get to my tagged commit by just looking at this tag, by checking out this tag. So I have happened to tag the top commit as the project tag, but if I do some other changes, like I make a new file and I add it, and then make a commit to record the fact that I've added this file, now my Git log has the new commit that I just made and still retains the tag on the whatever release I wanted to have before. So these tags are used for versioning, to keep track of the version history of your project. Yeah.
So when were we supposed to use Git to tag? Like when you said add, but before we said commit?
When do you add a tag?
Yeah.
So you add a tag, once you've done all of your committing, that means you've saved all the changes to the log of changes in your repository. Then you tag that version of the project that you want to be graded. So in this class, that's like submitting for a particular project. But in the real world, that's going to be like version 1, version 1.2, version 1.3. So there'll be some convention for version numbering. And that tag will will point to that version of the code that corresponds to that version number, that whatever your team decides on how they release versions and when they release versions and how they do the numbering system, that tag allows you to do version histories. Questions on this? Does this make sense? So anyway, I think the tutorial on using Git is fairly complete. But if you have issues with it, please feel free to talk to me and tell me what's missing or what was confusing or what didn't work. But in terms of submitting the project, if you run these commands, after you've committed all the stuff you want to commit, after you do that, then you tag with whatever, project 0, project 1, then you put the tag on. And that's it for your local repository. To get that information to GitHub, you push those tags to GitHub. So if you use an IDE or some GUI, this can be like automated for you with buttons and everything. But this shows you how the underlying tool, I think a little more at a fine grained level, shows you how what the tool is actually doing behind the scenes a little bit more. Questions on this so far? Questions? Yeah.
So whenever I was trying to use git tag, it said fatal tag already exists.
So that means you've already created the tag.
And where do I see that the tag though? Because when I'm looking at GitHub, it says there aren't any releases here.
So that means you haven't yet pushed the tags to GitHub. So if you do git push -- tags, those will be reflected on GitHub's version of the repository.
Okay.
But if you've already created a tag, Git will not allow you to just easily overwrite that tag. So if you want to force it to overwrite the tag, you can go to this section called resubmitting a project. And it's the same workflow, except you add this -f flag, which says force. So you force the tag to be recreated on a different version, different commit ID, a different version of the code. And you also have to force those new tags to be pushed to GitHub. Yeah.
Is it possible to remove a tag? Let's say,
You can remove a tag. So I don't remember the exact commands, but if you just Google it, git remove a tag, and go on Stack Overflow, it'll show you that. So how do you delete a remote tag? So there's a little rigmarole you got to go through in order to delete it from the remote repository, but it can be done. Yeah.
For your announcement that you put out about the make file and
Yeah.
it being on the top level, so that would need to be pushed along with the project.
Yeah. So the make file should be there as well. So yeah.
Two in there. I have three. I have the project 0.c, the make file, and the readme because it was just in there. Is that what we're looking for?
Yeah, I mean, so I think I kind of like to give a functional or operational definition of what the correctness should be. So I added a little section to the projects so that you yourselves can test the way we test. We'll have the automated script soon, so you can just run those when the graders are still working on them. But the way, not only in this class, but the way this should work whenever you're releasing software is you shouldn't have to handhold the user how they should use your software. If the only way your software works is on your particular machine and compiled with your specific set of commands, that's a pretty hard to use piece of software. So version control also makes this much easier to deal with. So what we're going to do in order to grade your project is we're just going to say git clone, whatever your project is. We know that from web courses. We're going to change directory into your project, and then we're going to run make, and that's it. So if that doesn't work on your side, then we won't be able to grade. Our grading scripts will fail, and you'll get a 0. But you can resubmit for a very, very lenient penalty up until the end of the semester. And then we're going to run the test as described elsewhere in this document. And the way you can verify this, and the way I actually do for my own software, like when somebody else is going to use it, I just clone a fresh copy of it, and I try to do the build. And whatever directions I have for using it, I try to just replicate that. So you can just go to a new directory in your file system. So don't go in your own repository, go somewhere else, and just reclone your project. So you can always always clone it to a different directory. So if I get the URL to my test project, I can give a new directory name to clone it to. So now, instead of cloning into, permission denied. This is because, sorry. So these are all my GitHub IDs. Okay, so I can just clone it into another directory. I don't have to clone it into project-_. So now I can see exactly what happens when I clone my project. So if you've forgotten something, you've forgotten the make file, then this will reveal it to you. An easier way to see if you've forgotten the make file is use git status. So I didn't explain git status in much detail, but in my git.md description, I just had you run git status over and over and over to see how the repository changes. So if I copied in my make file here and I ran git status, Git will helpfully tell me that there are some files that aren't yet being tracked by the repository. So this directory that holds all of these files, that's not the repository itself. The repository is actually inside of this .git folder. So this is really like the image of your repository, like the cave analogy. This is the image on the cave. The real repository is in this Git folder. And so using this git status command, it tells you the difference between the image of your repository that you have in your current folder and the actual repository log. Yeah?
So how do you know what repository you're cloning, to?
How do you know which one you're cloning?
So
That's given by this URL after the clone.
No, I mean how do you know where you're cloning your repository to?
How do you know where it's cloning to? This is the directory name after. So the first argument to clone is the URL. The second argument is the path you want to clone it to. If you have no path, by default, it'll go to the name of the repository, -.git. Yeah.
And to again with the tagging stuff, when you commit the tag, is it everything that was committed beforehand gets tagged, or is it something that would get committed at the same time?
No, it's whatever you committed before. So by default, it will commit whatever commit you're currently on, which is the last thing you committed. That's what's going to be tagged. So you could always explicitly say, I want to tag this version. This doesn't have a tag yet. I could tag it explicitly by giving the commit ID that I want to tag. So I tag it explicitly with something called new tag, and voila, I've got another tag on that commit. And if you push that to, so right now this is not going to be visible on GitHub because Git does not know about these tags yet. So I just say git push tags, and now my new tag is visible on the remote repository. So GitHub is just a way to easily kind of visualize your repository, but behind the scenes it looks much closer to what we're doing on the command line. Questions? Any more questions on this? So I was hoping to get this out of the way early in the semester, by getting you to clone your project and getting you to test out pushing. So I realized maybe not everyone was here on the first day when Mesut went over the Git using Git, but just follow that Git, or just use Google, and Stack Overflow will have every possible answer about using Git that you could imagine. Okay. So just keep in mind that if you haven't submitted Project Zero yet, or something went wrong with, you didn't have the make file, or don't worry about it. If you send me an email with it, I'm going to ignore it. I'm not going to accept submissions with email. So you learning Git is part of this project and part of this assignment, because this is system software. So why not learn some real world system software along the way? But my late policy is super, super lenient. You get, the projects are 12 points each. So if you're late by 2 weeks, up to 2 weeks, 1 point off only. And then you can submit it till the end of the semester for 2 points off. I think that's pretty lenient, right? So you can basically just do it at the end of the semester. And another thing to keep in mind is that Project 1 subsumes Project 0. So if you just start working on Project 0 and then tag them both, Project 1 and Project 0, you've done Project 0. So it's kind of it's a risk-reward trade-off. If you mess up on Project 1, then you mess up on both projects. But you could sort of kill two birds with one stone. Yeah?
So what about if someone was to upload the program 0 on time,
Yeah.
but there was something weird about how it was done and you guys weren't able to use it or some shit like that?
Yeah, if we can't grade it, then it's 0. But very lenient late policy. If this becomes an issue at the end of the semester, it's come talk to me if there's an issue. But yeah. So if it doesn't work for us, if we can't clone it and make it, then we can't grade it. But don't be scared. It's very lenient late policy. You can fix it, and then it won't happen again for the other projects, and then you'll know.
What should you see when you use make on it?
What should you see?
Yeah.
So you'll either see, what do you see when you run make? So in my little make exercise here, whoops. So if I haven't run make yet, and I run make, you'll see it build whatever C file you have in the directory. So as I described in lecture 2, I put that online, and I think some people may have missed that. I sent an announcement. But that went over make. So the make file I gave you will just build all the C files and then link them. That's what's going on here. So any C file that's in your directory will be built, will be compiled, and then they'll all be linked together into the simple C program.
So what do you guys do when you grade after that?
Then we just run simple C and run your tests. Yeah. So notice that if I run make again, it says nothing to be done for all, because as I described in that lecture 2, make is incremental. So if you make any changes to a particular C file, it will only rebuild that particular C file. Yeah.
So for Project 0, you can name your C file anything you want.
You can name your C file anything you want for Project 0. It doesn't matter. As long as, if you use this make file, then it just automatically builds for you the simple C program. Yeah.
So when we push our tag project to GitHub, will we see that in the code?
In the code? You won't see it in the code.
In the code tab on GitHub, or will we have to go to the...
You'll see it in the releases tab. The releases, you'll only see it in the releases tab. That's where you'll see the tag. So a tag is not part of the code. It's not really, in some sense, it's not even part of the commit history. It's a little table of names for particular commits in the history. Yeah.
So you keep referring to the make file?
Yeah.
And I tried to use the make file, and I don't know what I'm doing with it.
So check out lecture 2 online.
Lecture 2.
Yeah, lecture 2. Mysterious lecture 2. So I released it during the hurricane. but I did make an announcement.
And the actual thing we were turning in was the C program, not the executable.
No, not the executable. We're going to kill the executable. I don't want to make my graders have to run
All right.
arbitrary binaries.
So it's like I've got my tag built, and it's got its zip file, and it's my project, and inside of it is my my C program. So I guess I'm good.
You mean the source code of your C program or the binary?
The source code.
Yeah. Yeah.
The .c file.
Yeah. Yeah.
Okay.
All right. So let's move on. So, okay. I think you'll get it. You'll get it soon because you'll get a 0 and then it'll be instant feedback. But it's okay because it's very lenient late policy. And if it's a really big issue, if like everybody fails, then maybe we can rethink about the late policy for this one. But let's see how it goes. Yeah. 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 So yeah, if you get like 5 points on this one, you can resubmit it. We take the max. You resubmit it minus whatever the late thing is, take the max. So you can literally, like, as many people did last semester, just like submit everything at the end of the semester. You can do that if you wanted. If, you're adults, you can arrange your own time, for doing this. Just you got to get it finished by the end of the semester because I have a deadline for grades. Yeah.
I pushed the tag project and then I cloned it, the whole project, my project folder, and it's like big file.
Okay, so specific issues. Let's talk about it. The deadline's passed. It was 7:30, so it's gone. So talk to me in office hours next time, and we'll get you straightened out. Let's see how the grading goes on Saturday. So project 0, over for now in lecture. Let's move on to project 1. There's a lot more stuff to do, but come to me in office hours. Go to lab tomorrow, although Matsud will be talking about the stuff today. Go to office hours, and then we'll get you straightened out. Okay, so that was project 0. Let's move on to project 1. So it's very, very similar to project 0, assuming that you have all the infrastructure set up, all the tooling, make and Git and everything. But the definition of the project looks really, really similar. So I haven't talked too much about what this grammar means, but that's what we're going to be doing this week. We're going to learn what these formal grammars look like, how your compiler program will actually use this to be able to process programming languages. And in fact, they are technically could be used for human languages, although they aren't so much these days. So this looks very similar to Project 0. Does anybody notice, if anybody remembers the Project 0 grammar, does anybody notice any differences between these two? I think you were first. Yeah, go ahead.
So in Project 0, it was like number plus number, number minus number.
Yeah, that's good. So in Project 0,
recursively defined.
Okay, so you're already getting ahead of me. It's a recursively defined grammar. So in our previous grammar, as your classmate astutely pointed out, we just had each expression was just a number plus a number. But that's not very useful for doing a bunch of complex math. We're used to doing arithmetic expressions where we have parentheses and order of operations, and we can have these arbitrarily complex arithmetic operations. And the grammar on the left starts actually reflecting what that looks like. And in this lecture, I'm going to go over grammars and show you why this can express arbitrarily nested arithmetic expressions. That is exactly what your classmate said, because we can define this language of arithmetic expressions as this recursive nesting structure. So the project will be effectively the same idea as Project 0, except now we have to deal with these arbitrarily nested expressions and operator precedence. So before, you could only have one operator per statement, but now we've got a whole bunch of operations that can happen in a single statement. And so we're going to use the same kind of operator precedence that you're used to from math class, PEMDAS, right? So multiplication and division and remainder are at the same precedence level, so they're used left to right, and they have higher precedence than plus and minus. So I'll go into more detail about this today, actually. So if we have a program like this, just like we saw in Project Zero, except now we have arbitrarily long expressions, then our LLVM program will look fairly similar, right? We still have this multiplication operation. The difference is now we can have multiple individual operations for a single expression. So whereas before you had only one LLVM instruction for doing the math operation for each statement, now because we have an arbitrarily large number of operations in a single expression, there may be an arbitrarily long number of IR instructions that you have to execute. But I'll talk a little bit more about how to deal with this. Notice that we have to keep track of intermediate values. Kind of like if you're doing this arithmetic in your head, you're going to do 2 times 3 first, store that value somewhere, you're going to memorize it, and then do your final addition. You'll probably do that kind of naturally now, but we have to explicitly do this with the compiler. Okay, questions on that so far? Yeah.
So left and right parentheses are going to be new tokens that we're going to be...
Yes, that's right. Left and right are new tokens that we have to support. That's exactly right. There are 2 new tokens to support here. And notice that expression here. Is expression a token in this language? It's not a token, right?
It's an expression.
It's an expression, yeah. And so we'll learn today what that means, what these other symbols that aren't tokens mean in our grammar. Okay, other questions about Project 1, kind of the overall point of it? Well, I know we don't have so this week I'm going to give you the tools for actually doing this compilation, but pretty clear, right, what we have to do for it? Yeah.
So it's just adding, now we have to do expressions, like what we're doing from Project Zero, right?
Exactly, yeah. It's Project Zero plus expressions inside of the print statements.
We're going from 3rd grade to 6th grade now.
Yeah, that's right. Now your compiler is like, a 5th grader or something, yeah. Okay, so context-free grammars. So the whole, so last time we looked at lexing, where you just read in patterns of tokens, and then I kind of left it to you to have some intuition about how you could process those print statements in Project Zero. They were only print statements, so we could kind of intuit our way through it. But once we get these more complex languages, like these arithmetic expressions, it turns out that just recognizing these word patterns, these lexemes in the language, isn't really going to work, because programming languages have this nested structure. So we can have a while statement with some other list of statements inside. And inside there could be another if statement, there could be another while statement. Don't know why that's cutting out. There could be another while statement, and these can be arbitrarily nested. Regular languages cannot express this kind of nested structure. So the question becomes, how do we actually recognize these kinds of languages? We're going to have to do this for our nested arithmetic expressions. And if you were to sit down and try to do this with just lexing, like write a regular expression to match that, you would find that it's impossible to do. So just a little terminology note. I'm going to kind of use these interchangeably, but technically there's a distinction between parsing and recognizing. So the recognition problem is just checking whether a string is valid, checking whether an arithmetic expression is well formed, part of the grammar. Parsing is doing that, but also generating a parse tree for that. And we'll get into that today. So the limitations of regular languages. The classic example of this is the language where we have an unlimited set of nested matching parentheses. So, for us, this means we think of this as nesting, but the language is just if we have 3 parentheses as the prefix, we should have 3 parentheses as the suffix. So it's just this simple language where you have n number of parentheses and then n number of right parentheses. You have left parentheses and a matching number of right parentheses at the end. So it turns out this seemingly simple language defies regular expressions. You can't write a regular expression for this language. And if you ever did if you ever went on Stack Overflow and asked about parsing HTML or XHTML or XML using regular expressions, there's there's a meme on Stack Overflow about this question because it was asked so many times, and there's a sarcastic answer that's forever enshrined on Stack Overflow, mocking people who try to do this. And so the reason actually goes down to a pretty fundamental reason inside of this world of formal languages and formal linguistics. And we can actually prove this, as you'll probably do if you take big discrete, if you haven't already, is that you can actually prove that all regular languages have this property which is defined in the pumping lemma. So if the language is a regular language, that means it can be expressed with a regular expression, then it can be pumped. And intuitively, I'm not going to go into like the formal details of this or the proof of it, which I don't know if I don't think I can do this off the top of my head. But take big discrete and they'll go through all this. But the intuition is that if you have a regular language defined with regular expressions, for a sufficiently large string, you can pick out a section of the middle of that string and just repeat it over and over and over. And that is like all you can do to make new strings in your language. It's just repeated patterns of some middle section of like some arbitrarily long or some sufficiently long string in the language. So the intuition behind this, if you remember the automata, is that you have a finite set of states for your automata, but they have to recognize an infinite set of strings. So for a sufficiently long string, you'll eventually have to re-enter a state that you've seen before. Make sense? So if I have only 4 states, but I have 1,000 strings in my language, at some point I'm going to be able to find some string that has to enter the same state twice. So what this means is but strings like this, there are an infinite number of different strings without a repeating pattern in the middle of it. So because of that, we can't actually create a finite state machine that can recognize just matched parentheses. So I kind of rushed through that. I'm not really a formal algorithm guy. Big discrete will go into that in detail. But the kind of intuition of this is that we have a finite number of states, but we have an infinite number of states that we need to track. Questions on this so far? So I'd also recommend reading the Dragon book about this. It's in chapter 4, I think. I put the readings on the syllabus. I'd recommend reading that because it goes into a little more detail about this and about the pumping lemma. So to recognize this nested structure, just like lexers, we do the same thing. We have our formal language. So what is a formal language? Does anybody remember the definition of a formal language? Anybody? Yeah.
Strings over an alphabet?
Yeah, it's strings over an alphabet, a possibly infinite set of strings over a finite alphabet. So just like with our lexer, our parser is going to recognize the nested structure. It's going to read one symbol at a time. Now in formal languages, this is going to be some symbol from the alphabet. But for us, these are going to be the symbols recognized by our lexer, our tokens. So our parser is going to operate on tokens as if those tokens were like individual symbols in the language. So the lexer sees individual characters as individual symbols. That's their alphabet. But for the parser, it sees all of the tokens as its alphabet of symbols. So it's going to read one of these symbols at a time. Going to keep track of a look ahead, just like we did with the lexer. We're also going to match patterns of symbols, just like we did with the lexer. But when we encounter some nested structure, we're just going to save our current state onto a stack. And this is how we're going to capture this recursive structure of our language. So this is very, very closely related to recursion who here likes recursion? Is recursion fun? Who here doesn't understand it? Or maybe doesn't want to admit it. Who here hates recursion? Okay, so this class, I hope, will at least get you comfortable with recursion and not so scared of it. Because it's really not so bad. And in some ways, it's actually easier to solve certain programming problems with recursion. So this recognizing these nested languages is closely related to recursion. And as you might remember from an algorithms class, you use a stack you can either use a recursive algorithm or you can use a stack, right? Like for doing like tree traversal algorithms, you could either do recursion or you can do iteration using a stack. Did they teach this? Did you guys learn stack-based traversal? Yeah, so they're equivalent, right? And in fact, as we'll see later, functions are implemented using a stack. Recursion is actually implemented using a stack. So we can capture this nested structure by whenever we encounter some nested structure, we just save the current state onto a stack and start processing another set of symbols, another pattern of symbols. Oh wow, this thing's out. Can you hear? Oh, you can hear me. Okay, that is weird. And so in the formal languages world, or formal models of computation, this is called a push-down automaton. So before we had a finite state automaton, now we have a push-down automaton. All it is basically a finite state machine, an automaton, plus a stack. And so now we can actually, using this model of computation, this push-down automata, we can actually parse these nested structures. Just like we had regular languages and regular expressions are the same as automata, we have these grammars are the same as pushdown automata. Okay, so the way we express these, instead of using regular expressions, we use what are called context-free grammars. So this expression that is new for Project Zero, this is an example of a context-free grammar. And it captures the nesting of our expressions. So for instance, this expression on the right, this string in our language, it captures the nested structure of this expression. So 2 matches the number part of this expression, and similarly 3 and 4 match the number version of the expression. And when we see 3 and 4 together, which part of this expression does this match? Which pattern of expressions does this match? 3 plus 4. Expression plus number, good, yeah. So this matches the expression plus number part. And what about the sequence of tokens comprising left parenthesis, 3 plus 4 right parenthesis? Which part of our expression is matched by that? Yeah, good. L paren, expression, R paren. So we can see that expression just kind of abstracts away some sub-portion of this string. So expression can be any one of these possible choices. And if it happens to be 3 plus 4, then to match parenthesizing one of these expressions, we can just reuse the symbol expression to reflect any of these possible patterns of expressions. So I'll go into that a little more rigorously, what that looks like. But this whole notion of context-free grammars, just like before we saw this hierarchy of languages where we had regular expressions being the simplest and context-free, now we're at these context-free grammars. Context-free grammars or context-free languages subsume regular languages. So anything that is a regular language, we can also express using context-free grammars. But as we saw with the matching parenthesis language, the converse is not true. So just because something is context-free, we can't necessarily recognize it using regular expressions. And this actually goes back to work by Noam Chomsky, which I think I talked about a little bit before, who sort of founded a branch of modern linguistics where he tried to mechanically and objectively describe how language works in the brain. And he came up with this notion of generative grammars. And so his point of view, which is not necessarily the majority point of view in linguistics today, is that there's innate language ability inborn language ability, just like we have inborn ability to, our heart to beat or our eyes to move. Language, he proposes, is also this inborn ability. And there's somewhere in the brain that is actually processing grammar in the brain. And one of the intuitions behind this is that if we look at a sentence like this, so this is like Chomsky's famous sentence, colorless green ideas sleep furiously, versus furiously sleep ideas green colorless. So one of these, as you'll probably notice, kind of has a tinge of sensibility, right? Like the first one, even though it's kind of meaningless, we don't, you can probably ascribe meaning to it, but it's basically a meaningless sentence. But we notice that it's more syntactical somehow. We notice that it has kind of the right shape of a sentence. So this is part of the intuition behind like Chomsky's innate language ability. Also the poverty of stimulus argument, which says that children can learn to speak a language very fluently with very little examples. So for instance, in machine learning, you need a huge amount of data to train these statistical models. That's the behaviorist approach. And so the poverty of stimulus argument is one of the arguments. It's not a proof, but it's one of the arguments for innateness. Anyway, that's a tiny little bit of background, not my field, so feel free to go on Wikipedia, read more about this. It's a pretty interesting area. But it turns out that this work on grammars, whether it's biological or not, formalizes languages in such a way that they can be mechanically processed. And there was this kind of beautiful correspondence between these language models and models of computation for us. So regular languages, are both can be captured with regular expressions, which is the language model, but they can also be captured with automata, which is a model of computation. And context-free grammars can be captured with this other model of computation, push-down automata. So we can use this mechanical definition of language to very precisely define what our computer language is going to be, and then write algorithms that can automatically process these, which is exactly what our compiler is doing. So we can exploit these formalisms about language in order to write our compiler. So recall the definition of a language is potentially infinite set of strings over a finite alphabet. So the way we represent these nested structures is we give them a new kind of symbol. So in the lexer, we only had tokens. And tokens are always comprised of some lexeme, some subsequence of the string, some substring in the original input. So the regular language consists only of those actual symbols that are from the input. In context-free grammars, these are called the terminals. But to represent constructs, we have a new type of symbol called a non-terminal. And this symbol is not actually expressed in the actual string. It's not actually expressed in the language. So when you say a sentence like colorless, green ideas, sleep furiously, or whatever it is, the fact that there is a sentence there and there is a noun phrase and a verb, that's not expressed in the actual string of the language. But if we assume that there is some existing structure to that language somewhere, we can give symbols, kind of meta symbols, to describe those structures in the language. And in context-free grammars, we call those non-terminals. And so they represent the constructs, but they're not actually part of the string. And the way we describe the language is we define substitution rules that take these non-terminals, these kind of meta symbols, and break them down into smaller pieces of the language. So a sentence gets broken down into subject, verb, object. Subject gets broken down into noun phrase, and so on. And then the terminals of the language, for us, the tokens of the language, these terminate the expansion. That's why they're called terminals. So the non-terminals can be continuously expanded and broken down into smaller parts, and the terminals stop this expansion. And the terminals are the actual utterances of your language, the actual string symbols of the language. Okay, so to look at our grammar, expression is a non-terminal in our language. It's kind of a meta symbol. It just describes a set of patterns that the language can have, but the expression symbol will never actually be uttered. You'll never actually see it in the input in the programming language. Only the terminals, the tokens of the language, only those will be actually seen in the input file. And so I'm going to skip a demo and move on, because we'll do more demos about these grammars in a second. So the definition of a context-free grammar, there's 4 parts to every context-free grammar. There are terminals. These are the words, the actual utterances of the language. And for us, terminals are the output of the lexer. These are the tokens of the lexer. They can no longer be broken down into other symbols. They're the terminal parts of the language. The non-terminals are symbols that represent structures, and they can always be further broken down into some sequence of symbols, whether they're terminals or non-terminals. The rules that guide how these non-terminal symbols get substituted, those are called productions. And on the left-hand side, for context-free grammars, the left-hand side is a single non-terminal, like this, a single non-terminal on the left-hand side. And on the right-hand side, we have a sequence of terminals and non-terminals. So this production says expression can be substituted for another expression followed by the plus symbol, followed by the number symbol. So that's one production in our language. And we use a little syntactic sugar, these pipes, to just describe multiple productions for the same expression. And so this is where this is like similar to regular expressions where you can have alternation. Productions can have multiple different expansions. So one sentence in English can expand to, infinite number of possible sentences. One noun phrase can expand to lots and lots of different noun phrases, but it's a smaller subset of the language. There's only certain sequences of characters that are a noun phrase in the language. And so these production rules capture that. And then, of course, we have the starting symbol. So what's the starting symbol in our language, in our Project 1 language, if anybody remembers? Anybody paying attention? Program, yeah, program. Program is the starting symbol. So there's always a starting symbol. And that's like the top node of the language. That's like where you start doing this production. So that would be like, For English, that would just be like, I don't know, utterance or paragraph or something, or sentence, however you're defining your grammar. Okay, so a quick little review. Terminal versus non-terminal in our language. An identifier. Terminal or non-terminal? Who says terminal? Okay. Who says non-terminal? Okay, I tricked some of you. So an identifier, so I haven't really gone into identifiers much, but if you look at the lexical specification, an identifier is like a variable name or a function name. And they're terminals in the language. So they're actually in the input file. And they can't be broken down into any smaller parts. So in the lexer, they have their own definition. But for us, the tokens are the terminals of the language. So what about a statement? We've seen a statement in Project Zero. Is a statement a terminal or a non-terminal? Who says a terminal? What about non-terminal? Okay, good. Yeah, okay, they're good. So statement's a terminal, or non-terminal, oh my God, it's terminal. It can be broken down into smaller parts, into some other sequence of symbols. So program, terminal, non-terminal, okay, the semicolon, terminal, non-terminal. Okay, good. Yeah, I think you guys got it. So you can also see that I made a little convention here, that capitalized words are terminals, lowercase words.
Oh, yes, that first one.
So I do recommend that you read the Dragon book, particularly for this formal grammar stuff and some of the grammar hacking that we're going to do the next 2 lectures, because it explains it more in more generally in a more formal way. But the book will use a different notation for the grammar. So it's closer related to Chomsky normal form, which is Chomsky's like original description of these grammars. Non-terminals are uppercase, usually single letters. So E, would be an expression. Terminals are bolded words or symbols like plus and minus. Arrows are used to denote a production. So E can expand to E plus sign number terminal, E minus sign, blah, 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 blah. Pipe for alternate productions. And one thing to be careful in the Dragon book is that parentheses are not for like grouping. They're actually the symbol, parenthesis symbol. So this is the meta notation versus the actual language. The meta notation here is just the arrow and the pipe. Those are the only meta notation you have in this Chomsky normal form, as used by the Dragon book. I think the original Chomsky normal form is really just arrow, but the Dragon book does use this pipe symbol. So it's always, just like in a compiler, it's very easy to confuse the language that you're writing the compiler in versus the language that it's processing. We have the same confusion here, where we have, these are all symbols, and we're trying to mechanically define what these symbols mean. And in order to do that, we need new symbols to describe what our symbols mean. And these are our meta notation, and the meta notation of Chomsky normal form is the arrow and the pipe. The rest of it is just non-terminals or terminals of the language. So when you read the Dragon book, just be aware of that. They go over their notation, I think, in chapter 4. For this class, I'm using something that's a little closer to what compiler writers use. It's sort of like Backus, EBNF notation, extended Backus-Naur notation. Who's heard of this? EBNF? Anybody heard of this? Wow, one person. EBNF. So EBNF is extended Backus-Naur form. This is popular among compiler writers. If you look at the C specification, they'll use something that's a little closer to this, although not exactly. And I kind of use regular expressions as well. So some modern compiler generators will actually use context-free grammars plus regular expressions, because it just makes things more convenient to define. So for instance, program is statement star in my grammar, and that just means statement repeated 0 or more times. And so I use lowercase for non-terminals, uppercase for terminals. I use the equal sign for productions instead of the arrow. Pipe for alternate parentheses. But note that the parenthesis symbol, I use it for grouping things together, just like in regular expressions, not for the actual token or terminal. So all terminals are going to be lowercase words in our meta notation. So just keep that in mind. Reference this slide. It can get very confusing when working with these languages, because you're using a language to describe a language, and it can very quickly become mind-bending. Okay, questions on this so far, or questions about anything so far? Going through this pretty quickly. All good? Okay. So let's look at derivations. So the whole point of defining this grammar, at least for Chomsky and these innate linguists, is that this grammar is actually the machine that creates utterances in the languages. And the way that works is we start with our starting symbol and we follow the rules of our grammar, picking a production at each step and eventually creating some string in our language, creating some utterances in the language. So at each step of this generation, we pick a new non-terminal to expand, pick one production of that non-terminal to expand, and then just continue that process recursively until we get all terminals, till we get an actual string in our language. So I think it's easier probably just to demo this. So here is our grammar. Oops. Here's our grammar on the left, which is a little small. Cannot make it larger. There we go. No. Okay, that is a little small. Can anyone not see this grammar on the left? Okay. Okay, so let's say we have our string in our language, 2 star left paren, 3 plus sign, 4 right paren. So notice these are, these don't have any meaning yet. They're just symbols in our alphabet. To us, they look very much like arithmetic expressions, but we want to tell our compiler how, what this language means. So we can generate this string in our language by applying these substitution rules, these production rules. So we start at the starting symbol. So in this case, I'll just start at the expression and pick one of the productions to expand. So what's a little tricky about this process is it's very hard to know kind of ahead of time which production we pick in order to generate this sentence at the end. Although because of the parentheses, it makes it a little bit easier, perhaps. But what do you guys think? Anyone want to take a guess about what's the first production that's going to be applied when generating this string from this grammar? Anyone want to take a guess? Yeah.
I'm guessing if we're going like character by character, it's probably going to start off at just number.
Okay, so let's say if it just starts off at number. So our first production replaces expression with number. So then what is the next production that gets applied to substitute? Yeah.
L paren expression L paren, right? Or a few parentheses, right?
There must be a parenthesis in there, but notice we have reached, if we replace this with number, I think this is what we're going to say, we've already reached a terminal in our language, and there can be no more substitution because the terminals are the atoms.
So we're not reading from left to right right now, we're just literally looking at it as a whole instead?
Yeah. So this entire.
I thought we were looking at we're looking at just 2, and then we're going to look at 2 times, and then like that. So.
I see what you're saying. Yeah. So. So the expression represents the entire string. Actually, this is what makes it. This is actually what makes this tricky. So maybe another more precise way.
So in that case,
to write this.
It would be expression times number.
Expression times number. Okay, let's do that. So I'm gonna write this using the tokens to make it a little more precise. So I'm gonna call this LP num plus num and RP. So if you are confused about any of the way I wrote any of these tokens, I just abbreviated them, let me know. Just if you lose the plot or lose your way a little bit, just ask me. So once you lex, so we can say once we lex the lexer will produce this stream of tokens or terminals. This is pretty, so my writing is quite bad, but I will try to make this slightly clearer. Questions on this? Questions on this? So this is what the lexer would produce. Yeah.
Not a question on this, but your things about the guy. It says,
Oh. Thanks. Oh yeah.
Really, yeah,
15 minutes?
that's
Okay.
accurate. It'll die like right when class ends.
Now it's 14 minutes. Okay, let's see. Okay, I'll just get that ready. Okay, all right. So yeah, number will work because it's a terminal, and that terminates the substitution. So what was proposed next was we have expression times number. So this seems to match so far our string still. We have, just to very lightly put it, the number matches,
It matches the very first number.
oops. Uh-oh.
Expression is the 3 plus 4. The num is the 2.
I think I made a mistake in my expression. And I did. I made a mistake in the grammar. I hope nobody started working on project 1. So this grammar is supposed to be expression plus expression. My mistake. Uh-oh, that's bad. I'm so sorry.
Expression plus expression?
Yes.
So is that whole side?
Oh, I'm sorry, not plus, sorry, it's
Times.
times. Yeah, sorry. Times. So I will have to fix that grammar. And the way we can see this is that times maps to this token. So that means that this expression must somehow map to number, whereas the right expression maps to some other sequence of tokens. And so when we pick the next derivations, we can keep that in mind when trying to figure this out. So let's expand the leftmost expression. What will that be expanded to?
Num.
Yep, it'll just be expanded to a number because we have a production that expands expression to number. So this will be num times expression. And so how do we expand the next terminal? What num terminal do we have here? We have an expression terminal. So what will that be expanded to?
Left parenthesis, expression, right parenthesis.
Right, it'll be expanded to left paren, expression, right paren. Oops. So now we're sort of like gradually getting all the terminals in that correspond to the string in our language. What about this last expression, or this next expression? What does that get expanded into? So we've got our right paren, we've got our left paren, our times, and our number. So left we have num plus num. So what expression does that correspond to in my
Expression
in
plus
my
expression.
yes, expression plus expression. So now the next step of this derivation is num times LP. Whoops. Expression plus expression R paren. And so on. And then each of these expressions, the final derivation that we have to do is replace each expression with a number, and we get the final string in our language. Questions on this so far? Yeah.
So that very last line, what
Because I made a huge mistake in this grammar. This is supposed to be expression plus expression.
Oh.
That's why. So this is supposed to be this. So I'm terribly sorry about that. I'll fix the assignment online tonight. So this is what the real grammar looks like. Instead of numbers, we have expressions plus some other expression. So that way you can have an arbitrary nesting depth on either side of each operand. Oh boy, that was bad. Sorry about that. What's that? Oh yeah, sorry. So let me move this over here. And if we continue this derivation, and so on. And finally, this expression gets replaced with a number. And we get the exact string that we read in. But yeah.
Did we start with anything before expression times expression?
We started with expression. This was our starting symbol.
Okay. Did we say like expression meant number at some point?
Yeah, that's here. So maybe I can actually, might be useful to skip ahead to derivations as trees since we don't have much time. Another way to, so I'll show this derivation again in a way that I think is kind of makes more sense to me, and it makes more sense for parsing. So just be aware when you read the Dragon book, they're going to talk about leftmost versus rightmost derivations. Leftmost just means you pick the leftmost non-terminal to substitute first, always. So in our derivation, we always picked the leftmost. Whoops. We always pick the leftmost. We always pick the leftmost expression to substitute at each step. That's all they mean by leftmost derivation. Yeah.
So when you're like reading, so in project 1, do we still have to read character by character, or is it just like?
No, since you have your lexer already, your lexer will be producing tokens for you. So you can treat these if you wrote like I suggested two ways to do it. So if you wrote just a lexer that produces a stream of tokens, like an array of tokens, you can just use those array of tokens to iterate over. If you wrote a function per token, then you can just call that function, and that's your terminal of your language. Okay, so yeah, just be aware of that, leftmost versus rightmost derivations. So the parsing problem is the derivation is going from, is producing a string from the grammar. That's what the generative grammar is. You have some grammar, and you can use it to produce some arbitrary set of possible strings. Parsing is the inverse problem. Given some string in the language, like an input, like a C program or an input file, what is the set of derivations that led to that? That's kind of what we had to do when we generated that derivation. That's what the parsing problem is. Yeah. My laptop's what? Oh yeah, I plugged it in. Let's see if it's charging. Yeah, it's charging. Thanks. So that's the parsing problem. And for me at least, I find it helpful to represent these derivations as trees. And these trees are called parse trees. So the root node is the starting symbol. Each inner node is some non-terminal, and then the children of those non-terminals, that's the production rule, basically. And then leaf nodes are your terminals. So let me go through that same example using a parse tree instead. Makes it a little easier on myself. So remember, so we had Let me just write the token input for this string. Okay, there's the input token in our string. We start at the expression non-terminal. And so if you remember our derivation, we first derived expression times expression. This was this first production rule that we applied. And so notice that we've already reached a terminal, so we can just draw a line from the expression to the actual terminal token from our input. And continuing this leftmost derivation, expression, there's a production rule that substitutes an expression with a number. And then what was the production rule we used for this expression on the left, this expression? Right, it was L paren, and L paren was followed by an expression, and then R paren. So you can see with this tree, we're sort of recording all of these derivations in this nice tree structure that's reflecting this nesting structure of our language. And then the next production that we applied. So expression, I think I heard expression plus expression, and then we just apply the rule that substitutes a number for an expression. And now we get a parse tree. We get a parse tree for our language. It's equivalent to a derivation in the language, more or less. Questions on this? Questions on the parse tree? Okay. All right, so it turns out in this grammar is actually an ambiguous grammar. There are multiple derivations or multiple different parse trees for the same string in the language. So for example, if I have 2 plus 3 times 7, no parentheses, there are actually two ways, semantically there are two ways to interpret this, right? If you have a little desktop calculator, if you say 2 plus 3 times 7, what are you going to get on a simple, cheapo desktop calculator without order of operations? What will you get? What number will you get?
35.
Yes, right. Yeah, 35. It took me a second to. My math is bad. So yeah, you'll get 35 if you do the plus first. But if you have a nice fancy graphing calculator that respects order of operations, or you use C, what are you going to get? Yeah, no, that's not 40. 43. Is it 42? 42. 23. Ooh, my math is bad. Yeah, 23. Ooh, that's why I'm in computer science. Let the computers do it. So anyway, yeah, there's two ways to interpret this. And in the definition of the language that I just corrected for you, there are actually two ways to parse this. There are two possible derivations for this same string. So let me show that to you now. So if I've got 2 plus 3 times 7, that would be num plus num times num. And I'm going to, whoops, I drew times there. So I'm just going to make it a little clearer for myself, I'm just going to assume that you're going to tokenize it in your head, because this is just easier to write. All right, so there are actually two ways to parse this string. So what's one way? What's one derivation of this string? Well, what's the first production I would apply? Plus or multiplication? All right, let's say we do plus first. So there's one derivation where we do expression plus expression. And if we're doing a leftmost derivation, this expression gets substituted with a number. And what about on the right-hand side? What's the production that gets applied? Expression times expression. And these get mapped to their corresponding numbers. But if we happen to choose a different production as our first step, we would actually end up with a different parse tree. So if we chose multiplication first, and followed this through, so then we do the addition second, we would end up with actually a different parse tree. So this is the definition of an ambiguous grammar. If for a single string you can find two different parse trees for it, then the grammar is ambiguous. Equivalently, that's equivalent to saying if there are two different leftmost derivations, because parse tree is derivation, then the grammar is ambiguous. And for us, what this means is that for our programming language designers prefer not to have these kind of ambiguities in the language. I mean, you can imagine that if you did 2 + 3 × 7, and one compiler said, 23, the other one said 35, not a very portable piece of code. You probably want to pick one. And so most languages today, actually with the exception of Fortran, which does not have order of operations, it will just do left to right like a desktop calculator. Most languages today will respect order of operations. And so it turns out that you can actually solve this problem. One way to solve this problem is to rewrite the grammar so that the grammar enforces the order of operations. So this is actually your homework to do. I was going to go over this more in class, but I don't think I have time, so I'm going to leave it as a harder homework exercise, which you can actually just look in the Dragon Book and it tells you the answer. So rewrite our grammar, our expression grammar, so that it enforces order of operations. And look in the Dragon Book, it'll tell you how to do it. If you can't do it, it's okay. Just make an attempt. So the homework is write the grammar with operator precedence and do some derivations. If you can't get it, that's okay. We'll go over it next time. It's actually due in a week, so you can wait. But yeah, you basically just add extra non-terminals that reflect factors and terms instead of expressions. And I'll let you discover that. We'll talk about it next time. All right, thank you, everybody.